I must confess to a certain amount of whimsy and indiscipline when I was creating this portion of the lecture. The images you see on screen are playbills for the 14 Gilbert and Sullivan comic operas that were produced between the years 1875 and 1896. These were written by the great comic librettist William Schwenk Gilbert, and the musical score was arranged by Arthur Sullivan, and of course these are now the Gilbert and Sullivan operettas. I must confess that I actually had a more portentous example in mind to create for you today. But one of my daughters called me out when I was preparing the lecture and said, "Oh, you're not really preparing a lecture, you're actually playing and looking at these Gilbert and Sullivan playbills." This is true. This was indiscipline on my part. I played hooky and I started looking at these playbills from over the internet. I happen to be a huge Gilbert and Sullivan fan, and so yes, I was being indisciplined. But having done this, I've got these playbills up on my computer screen. I said, well, I've got to justify the investment in time. So I changed my mind and I decided to create an application where at least these playbills come into play in the context of this Poisson sieve that we've been talking about. So, if you'll indulge me, there's a little bit of whimsy here. This is going to be related to another classical and beautiful problem, which has echoes in subtle modern applications. So let me give you a clean version of the problem. This is called the coupon collector's problem. And let me put this in the context of the Gilbert and Sullivan playbills in the following light. Let us say that a novelty manufacturer, perhaps in London, faced with falling sales of his novelty items, decides to try to capitalize on a feeling of nostalgia current in the population at this time. And to incite people to buy his novelty goods, he insets with each good a coupon, a playbill of an original Gilbert and Sullivan opera. These playbills are chosen at random and inserted into these pieces of merchandise that you purchase. Of course, an emotional public flocks to this manufacturer and starts buying these novelty gadgets in large numbers, hoping to collect all the original Gilbert and Sullivan playbills. Of course, we want to properly abstract away the trappings of this problem. Imagine that instead of these playbills, we have N coupons, N collectibles. Of course, these could be the Gilbert and Sullivan playbills, but you could replace them by anything else that strikes your fancy. G.I. Joe figurines, baseball cards, cricket cards, images of soccer players, football players, what have you. You have N coupons, and coupons are selected randomly and inserted into merchandise. When you purchase a piece of merchandise, you hurriedly open it and see what coupon is inside it. Well, what is your objective? Of course, you'd like to get all the coupons. You'd like to get all the playbills, all the figurines, all the baseball cards. Now, let us say that in your first flush of enthusiasm, you go and buy not just 1 or 2 or 3 pieces of merchandise, you buy, let's say, T units of merchandise. And now our questions are going to be related to, if you buy T pieces of merchandise, how many distinct playbills, coupons, figurines did you manage to collect in that time? Of course, the luck of the game would mean that you pick up some particular coupon and then in several other purchases you happen to get the same coupon. Bad luck. But if you purchase enough pieces of merchandise, then with luck you will eventually get all the coupons or most of them. So, how many distinct coupons do you get after T purchases? Of course, we discount multiples of the coupons. We want distinct individual coupons. How many? Oh, here's another question. If you really are insistent upon collecting all the N coupons, how many purchases do you need to make before you can do this? Of course, this looks like an amusing little problem of no great moment, but nonetheless, it gives us a beautiful vehicle for investigating what our substratum, our theory, leads us towards? Of course, it's a chance game. Right? We've simplified the problem. We've assumed that all the coupons are equally likely, and each of them is equally likely of distribution into any given particular piece of merchandise, that the manufacturer has got an infinite supply of these coupons available, so he can keep putting coupons in without denuding his supply. And what is the chance experiment here? Well, naturally enough, our very first question is going to be inevitably, what is the sample space for the problem? And the moment you do this, you realize, well, what have I done? I purchased T pieces of merchandise. With each piece of merchandise, I picked up a coupon, a playbill. The entire chance experiment is completely specified as far as our interests are concerned in the particular coupons that you picked up in your T purchases. In other words, the sample points are going to be adequately described by a T tuple of integers. Label the coupons 1 through n and specify a T tuple where each of the elements k1, k2, k3 through k sub t represent numbers from 1 through n. They represent which coupons you got on which purchases. And this ensemble of purchases tell you all the coupons you've acquired over T purchases. Of course, there could be duplications of coupons in these purchases. So sampling is implicitly here with replacement from an underlying population. Things can be repeated. All right, now we've got a T tuple of coupons, sampling with replacement. What is the underlying probability measure? Naturally, inevitably, it's going to be combinatorial. Every T tuple has the same chance as every other T tuple. But look at our game. What are we doing here? We're selecting a coupon at random for the first purchase. That's what we get. We're selecting a coupon independently at random for the second purchase, independently at random for the third purchase, for the 10th purchase. We've got a setting of repeated independent trials. Of course, this is going to make it very easy. The combinatorial measure is going to place equal mass on these objects. Each of these coupons has got a chance 1 in n of being selected on each trial. Therefore, a given selection of coupons has got probability by independence. We have a product measure 1 over n to the power t, or simply the reciprocal of n to the power t. Excellent. What now are the events at hand? Let's take a good look at this. Naturally, the events of interest are whether I acquire the first coupon or the second coupon or the third coupon and so forth over T purchases. What is the bad event? That I don't acquire a particular coupon after those T purchases. So let's promptly give it a name. Let A1 be the sad, unfortunate event that after T purchases expended, I have not acquired the first coupon. Let A2 be the event that after T purchases, I have not acquired the second coupon. Generically, AJ the event that after T purchases, I have not acquired the jth coupon. Now, we could write down a subset of the sample space corresponding to this, but I'm not going to do this because now it's clear what we're going to need. A sub j is the event comprised of all those T tuples of integers from 1 through n where none of the elements in the T tuple is j. Because if you did, then you'd have acquired the jth coupon. So you're looking at all T tuples where you avoid j. Let's promptly put in place an indicator for this unfortunate sorry event. Let x sub j be the indicator for the event aj. X sub j is 1, means that in T purchases you have not acquired coupon j. Now, with these basic events, what are the general events of interest to us? Well, the first event is that in T purchases, I am lucky enough to get every one of the coupons, the playbills that I'm hoping to collect. The event that I get coupon 1 is A1 complement. The event that I acquire coupon 2 in T purchases is A2 complement, and so on, and therefore the event of interest is the intersection of these complements, this is the good event. The events A1, A2 are the bad events, the complements are the good events. And I'd love dearly to figure out what are the chances of the good event occurring, that I get all the coupons. In terms of the indicators, this is equivalent to the event that the sum of the indicators is 0. If the sum of the indicators is 0, that means that none of the bad events happened, which means I've managed to acquire all the coupons. And more generally, of course, we'd like to know the chances of not acquiring, say, k coupons out of the n. And this is then the event at hand, where the sum of the indicators is exactly k. Before we launch into the analysis, it's not going to be hard, okay, but it's going to require setting it up carefully. Let's take stock of these events, right? Individually, the events seem to be fairly easy to characterize. The difficulty, of course, is that these events are not independent. If you've acquired the first coupon, then you know that at least one of the purchases cannot be allocated to the second coupon, and perhaps more if the first coupon were duplicated or triplicated, which means that you have fewer chances to get the next coupon. And each new coupon you acquire reduces the chance of acquiring the remaining coupons. The events are, sadly, dependent. But we also anticipate that the level of dependence is not significant. And this, as we shall see, will indeed be the case. Things are all set up for an inclusion-exclusion argument, so let's promptly set this thing up. We want to figure out the inclusion-exclusion sums S1, S2, S3, S4, and let's start with the simplest case again to settle intuition, the very first term. What does this involve? This involves figuring out the probability that a particular coupon is not acquired. Let's pick the first coupon. What is the chance that in tea purchases we do not acquire the first coupon? Well, the very first Gilbert and Sullivan opera was Thespis. What is the chance we don't get the playbill for Thespis? Well, this is easy enough to figure out. This means that we're looking at T tuples of purchases where none of the elements in the T tuple is 1. The probability that a particular purchase lands the first element is 1 in n. The probability that a particular purchase does not land the first coupon is 1 minus 1 in n, an elementary use of additivity. By independent trials, the probability that in t independent trials we do not acquire the first coupon is 1 minus 1 over n to the power t. Of course, this argument is impeccable for any of the coupons by the symmetry inherent in the problem, and therefore the first inclusion-exclusion sum S1 is simply n times 1 minus the reciprocal of n to the power t. We're not going to try to simplify it at this point. Let's build more ammunition before we come back and say, well, what is this strange thing behaving like? What can we say about the second term? Well, pick two generic coupons, let's say 1 and 2. What are the chances that we're unlucky enough to not acquire either 1 or 2 in T trials? That is the probability of A1 intersection A2. Well, that means the chance of acquiring on a given purchase one or the other of these two coupons is 2 in n. The chance of not acquiring either of them is 1 minus 2 in n. And the chance of not acquiring either of them over t independent trials is 1 minus 2 over n to the power t. Again, the calculations are impeccable for any pair of coupons, and therefore the second inclusion-exclusion sum S2 is given simply by n choose 2 times 1 minus 2 over n to the power t, or in terms of the falling factorial notation, n to the 2 falling over 2 factorial times 1 minus 2 over n to the power t. And now we're all set. What are the jth term? Pick any j coupons, for definiteness, the first j coupons. what is the chance that in T purchases, none of the first j coupons are required? And now we know exactly how this is going to go. The chance that on a given trial, none of those first j coupons is required is 1 minus j over n. The chance that this unhappy event happens in T independent purchases in a row is 1 minus j over n to the power t, and therefore the corresponding inclusion-exclusion sum S sub j is simply n choose j times this quantity, and we'll simply write it out in falling factorial notation as n to the j falling over j factorial times 1 minus j over n to the power t. Now we understand the generic term. It's a little more complex than what we saw for the problème des rencontres. But no matter, it's still an elementary functional form, and with luck, if we're good and say our prayers at night, this might fall into a lapse in some nice and compact way. Let's take a look. So we want to look at the inclusion-exclusion sums, and we've got an explicit formula for it. Admittedly, it's looking more cumbrous than we would like. But let's take a look at that power. T is some fixed number. I'm going to hold that for the time being. N I'm going to think of as a large number of coupons. So what I've got is 1 minus some constant j over a large quantity to a given power. Have I seen anything like this before? Maybe in an elementary calculus class. As you scratch about in your memory banks, you might actually stumble upon the following observation. This actually looks like an exponential. Remember that if you look at 1 minus x over n, the whole thing to the power n, think of x as something fixed and n is large. In the limit as n goes to infinity, that quantity goes to e to the power minus x. In fact, one could use this as a definition of the exponential function. That's one of the alternative ways of defining it. Okay, so here's a fact from calculus. Now I've got something which is reminiscent of this, except I don't seem to have a power n in the power. Let's simply add it in there by multiplying and dividing by n. Now what do we have? Well, we have the binomial coefficient in front. 1 minus j over n to the power n times t over n. To the power n, we can now approximate by an exponential function with an exponent minus j. And then we're going to have to take the whole thing to the power t over n to make up for the extra term I had to add. And there we go. Now you take a look at this and say, well, very good, this is an approximation to be sure, but it's going to be pretty good for large n. We now have something in the numerator which looks like a power of j. N to the j falling is going to be approximately n to the power j for large n and modest j. And then we have an e to the minus t over n to the power j. Well, let's group the power j's together, purely algebraically. And now in the numerator, in the round brackets, we have n times e to the minus t over n, the whole to the power j. In the denominator, we have j factorial. Now, a student might well be forgiven for saying, okay, he's doing algebraic manipulations and strange things are happening and I don't see where this is going. But at the end of all of this, when the dust has settled, what have we done? An inclusion-exclusion sum on the left is approximated by a power over a factorial. You say, oh, wait a minute. That's exactly what the Poisson sieve required. Let's formulate this. If the thing in the numerator in the round brackets on the right, if that behaves like a constant, say lambda, then I've got exactly a Poisson sieve paradigm. And here we go. If n times e to the minus t over n is some given constant lambda. Remember, what do we have that we can play with here? Well, we can play with the number of purchases t. Remember, n is some large but fixed quantity. We can play with a lambda. That's a constant I can choose. If I'm going to play with the number of purchases, let's rewrite this expression in terms of t by taking logarithms of the two sides and then reassembling things. I find that t is n times logarithm of n over lambda. The logarithm is to the natural or Napier base. If the number of purchases satisfies n times logarithm of n over lambda, or the nearest integer to it, then the inclusion-exclusion sum Sj behaves like a power of lambda over a factorial. and bingo, we've got it. We've got a Poisson sieve. Now, if this is the case, let's quickly run through the calculations and then run a slide over what we've discovered. What about the probability that we acquire every coupon? This is the good of it. Well, that's an inclusion-exclusion sum. But the Poisson sieve is going to tell us that this is going to behave like e to the power minus lambda. If t satisfies n times log of n over lambda, then the chance of getting all the coupons in your t purchases is approximately e to the power minus lambda. Of course, because I'm greedy, I want to have a high chance of getting all my purchases. This e to the power minus lambda stands in the role of a confidence parameter. I would like it to be high, near 1. That gives me a lot of confidence that with this many purchases, I've got greedily all 14 Gilbert and Sullivan playbills. Let's take a look at what it says more generically. What are the chances that exactly k of the playbills stubbornly refuse to be obtained in my t purchases? So in t purchases, I've acquired n minus k of the playbills, but there are k of them which I have not sadly been able to get. The Poisson sieve tells us immediately that this is going to be approximately e to the power minus lambda times lambda to the power k over k factorial. Let's put some numbers on this just to settle the concepts. At this level, you should take a look at this and say, I had a problem which was not very complex in statement. The analysis was tricky and ended up with inscrutable sums which I had no feeling for. But the Poisson sieve says each of these sums behaves like this very simple Poisson character. And that can immediately now allow us to draw conclusions from this. So let us say that I want a 90% chance of getting all the playbills. There are 14 playbills at hand. How many purchases do I need? Of course, this is the million-dollar question. How much money am I going to waste in searching for this will-o'-the-wisp? If I want a 90% confidence, then I want my e to the power minus lambda to be about 0.9, or lambda to be about 0.1. And if lambda is 0.1, then the number of purchases t, per our beautiful simple prescription, should be n times log of n over lambda. N is 14, lambda is about 0.1, and you find that I need about 69 purchases to guarantee with a 90% confidence that I've acquired all 14 original playbills. What if I want a much higher degree of confidence? I am a Gilbert and Sullivan fanatic. I really want all of them. What if I want a 99% chance? How large will t have to be? If my confidence e to the power minus lambda has to be 0.99, then lambda is 0.01. T, n times log of n over lambda with n 14, lambda now 0.01, now clocks in at 102. I'm going to have to pay a price if I want an incredibly high confidence. I'm going to have to buy a lot of playbills. And of course, the last very many of the merchandise pieces I'm purchasing are all hunting for the last elusive playbill. And as you know from your experience, the last item that you haven't got yet is going to take you the most time. And that's where we're going to expend our time. So if I want a 99% confidence to get 14 items, I'm going to have to buy more than 100 pieces of merchandise. Admittedly, this was a little whimsical, and I must apologize for my indiscipline. I wanted to show you something weighty and portentous involving internet security, but I thought this is fun, and I couldn't resist it. And it tells a story, and it shows you how we can implement the inclusion-exclusion ideas elegantly and simply. This concludes this lecture, and now we'll go on to summarize what we've discovered in this last tableau. And in the summary, I'll then show you where these discoveries lead today and to the kinds of rich applications that they inform.